はい、おはようございます。お待たせしました。ロボカップアジアパシフィック2021アットホームシミュレーション SOPL のリーグですけれども、本日最終日ということで、テクニカルチャレンジのプレゼンテーション競技を、9時からスタートしたいと思います。今、開始4分前ということになりましたので、ライブストリーミング、開始しましたが、はい、おはようございます。お待たせしました。ちょっと待って。ちょっと待ってくださいね。どこで羽織ってんだ。すみません。私が羽織らせてしまいました。これで大丈夫かな。はい。改めまして仕切り直します。すみません。私司会務めさせていただきます国立情報学研究所の稲村と申します。よろしくお願いいたします。で、今日のテクニカルチャレンジというのは昨日までの、ロボットの知能アビリティをこう評価するっていうのとはまたちょっと違ってですね、各チームからいろいろな未来に向けての提案をするプレゼンテーションをしてもらうというような、競技のスタイルになっています。いわばアカデミックな研究の発表をするというような形も含め、未来こういうような将来が展開できるだろうという提案をしてもらうという趣旨のプレゼンテーション競技になっています。1チーム15分のプレゼンテーション時間があって、その後5分の質疑応答をする。で、今日は3チームから3つのプレゼンがあるというような形です。で、今日はですね、今先生方の顔が映ってますけれども、各先生から6人の先生、に審査員として今日は来ていただきました。この画面の順番でいきますと、まず一番左上の画面に映っている野田先生ですね。北海道大学の野田樹先生です。もうロボカップの世界のロボカップの理事も務められて、人工知能学会の会長とかもう私が紹介するともう長くなってしまうので、ちょっと時間の関係で省略させていただきますが、もうロボカップの創立から含め、ずっとサポートしていただいている大御所の先生でございます。よろしくお願いいたします。
お願いします。
はい。で、次右上ですね。右上の谷口、先生、立命館大の谷口先生にもお越しいただいております。ありがとうございます。谷口先生もロボカップのエデュケーション OPL、最近もう非常に大活躍しているんですけれども、今日はシミュレーションの方でもちょっと審査に加わっていただきたいと思っております。はい。それから次、中の段に行きまして、Thank you for your contribution, Professor Sakvichai from Thailand. He is also always contribute to the RoboCup competition, but this is, I guess, the first time to join to the simulation league. So please judge the presentation from the viewpoint of both of simulation and the real application. はい。で、私の下に見えてます松坂様ですね。株式会社 MID の方で、この SOPL とは別にもう一つのサブリーグ SDSPL のシミュレーターを開発されていらっしゃる方になります。はい。そういう形でもうシミュレーションの方からも評価をしていただければと思います。あと江口恵美先生、右の真ん中の段ですけれども、ジュニアロボカップのジュニアの方でもう昔から非常に活躍されてきて、若い人たちをもう引率してエンカレッジされている先生になります。恵美先生にもそういう形で子どもたちの視点というかジュニアの視点からでもちょっと審査に加わっていただければと思います。それからDr. Lucia from Jupiter Robotics. She is working at the Jupiter Robotics. So we invite her from the viewpoint of industrial field. So not only the academic field aspect. So please judge our presentation from the viewpoint of the possibility or feasibility at the industrial and the real application. Okay, thank you. はい、それではですね、そろそろ時間になりましたので、プレゼンテーションの方を進めていきたいと思います。よいしょ。で、今これ、Zoom の画面には審査員の方が基本的には入ってるんですけれども、はい、今2人入ってきました。これが最初のプレゼンテーター、カメライダーのチームの2人になります。 でちょっと今競技時間を押してますけれども、あと 1,2 分で開始したいと思います。カメラです。Can you hear me?
Yes.
はい。OK。じゃあ、Your presentation is 15 minutes. And please use the screen share function of the Zoom presentation. Okay, are you ready for the presentation? No problem. Camera riders, are you ready for the presentation?
1 minute.
If you can, you can start your presentation. Are you ready? So, but this is a time schedule, so I'd like to start the stopwatch. I'm now starting. So please finish your presentation within 15 minutes. Hi, the presentation is started.
Okay, hello and good morning. So we are Kamen Rider from UTHM RoboCup from Malaysia. Okay, this is our technical challenge project. So our title is Sign Language Trainer in Virtual Reality VR. Okay. Okay, sign language are developed primarily to aid deaf and dumb people. They use a concurrent and specific combination of hand movement, hand shape, and orientation in order to convey particular information. One such set of language is the Malaysia Sign Language (AIM) system, which is predominantly used in my country. The main purpose of the sign language are to provide speech and text output using hand gesture sign language without using any sensor for dumb people in smart way. Okay, this is our problem statement. Due to pandemic COVID-19, we have difficulty to meet people face to face. We just contact with people through media social, like having a video call or virtual meeting. Also, we must practice social distancing in order to prevent COVID-19 from spreading. So we didn't have so much opportunities to learn sign language. To learn the sign language, we need professional guidance to do the sign language gesture, so we can get more accurate data. The information data that found on the internet does not meet with the IM standard, since the sign language got so many versions from other country. Okay, this is our method. So the method for this challenge is first to record the hand gesture from VR, and then we collect the data from the hand gesture from VR, and the last we will get the data and train it. Okay, this is our short demo video. Okay, our goal for this challenge is this, to make the data of the sign language that can be applied into the real physical robot. It also can make humans to communicate with the real life robot by using sign language. Next, it will save energy and time, especially due to this COVID-19. It will enable for the professional interpreter to teach people who live far away. So we hope it can collect the valid data to get the valid data from the professional interpreter in order to get accurate data for training purpose. Okay. That's all from us. Thank you.
All right, thank you. Is it the end of the presentation, right? Okay.
Yes.
Hi. We have 5 Q&A time, so the time is a little bit short for the presentation, but we have to finish within 5 minutes for the discussion. So if you have a question, please raise your hand, please ask directly. Okay, just start of the discussion time. Hi, start.
Okay.
Hi, Noda Sensei.
I have a question. So thank you very much for your interesting presentation. And this system is quite seems quite effective for disabled and communication with disabled. So one question is how to get feedback from normal people that learning sign language. So now I can see the shape of the hand, but in order to improve my skills, so I think the system needs some feedback mechanism from users. Could you, do you have any plan about this side?
How we can get a feedback from the user is from the data set. Actually, the when we do the sign language, the Unity will get the data. The every joint will get the output data.
Okay.
It will display in the Unity site.
Okay, I see. Thank you very much.
Hi, thank you. Are there any questions? We have 3 minutes left.
Maybe this is a very simple question. So thank you for your presentation. So to obtain this kind of data set about the sign languages, it's gesture. So what is the key difference between using this kind of simulation virtual environment and just taking how to say data without this kind of simulation environment?
Okay, in this pandemic, we cannot meet people face to face. Okay, so by using this VR, the professional interpreter can do the sign language remotely. So we can record the data from here, and the interpreter will be stay at their place.
Thank you very much.
Thank you. So do you have any additional question? We have 2 more minutes.
I have a question.
Hi, please, Matsusak-san.
I heard in some sign language research, some information like facial expression is important rather than the hand gestures. So how do you think about those additional information that might be effective for human to robot interactions. How do you realize them in the virtual environment?
For now, we just we just do the hand gesture. So actually, the motion also important in the sign language to expose our motion, our expressive to people. So for the improvement in this challenge, we will do the full avatar to get the hand gesture also with the motion expression.
Nice. For features that you are planning to use, hold the avatar.
Yeah.
Okay, thank you.
Okay, we have 30 seconds. Do you have any short question? Okay, it is almost the end of Q&A time. Okay. Hi. Hi, it's the end of the QA time. Hi, thank you for your presentation, Camille Leaders. Hi.
Thank you so much.
はい。じゃあ先生方もありがとうございました。Thank you for your Q&A. Please log out from the main loop. よいしょ。Okay, then now I would like to invite the next presentation. So please wait a moment. 松坂さん OK だな。よいしょ。ソビッツの2人を今インバイトしましたが、入れてますか？聞こえてますか？
はい、聞こえてます。
はい。で、プレゼンテーションは20分からなので、定刻通り来たいと思いますので、ちょっと5分間お待ちください。先ほどのカメライダーのプレゼンがかなり早く終わってしまったので、ちょっとオンタイムで来たいと思います。9時20分まで少々お待ちください。ソビッツのチームは準備モードで、スタンバイしていてください。The first presenter and the short, so the time is a little bit earlier than the schedule, but we will wait for the original schedule. So we'd like to start the presentation from 9:20. Okay, so please wait for a while. Then next presenter, Sobit, is now preparing.じゃあ審査員の先生は先ほどの違うか審査員の先生はこの時間を利用して先ほどのちょっとプレゼンの評価などを始めておいていただければと思います。よろしくお願いいたします。で大変アナログですけど。でめちゃくちゃアナログですけどこのタイマーを見てるので、あと何分っていうのはこの辺でこう私がちらっとやるのでソビッツのチームはこれ見てください。本当はこれもデジタルでこれはデジタルですけど画面に出てくるとよかったんですけどあと私こうしますので、はい、見ててください。はい、YouTube ご覧の方は今ちょっと次のプレゼンの、準備時間に入っています。最初のカメライダーのチームからのプレゼンテーションが、かなり予定より早く終わったので今オンタイムで次のプレゼンに行くということで、あと3分ほど お待ちください。9時20分から定刻予定通り9時20分から2番目のソビッツチームのテクニカルチャレンジの発表を進めたいと思います。ちょっとこの時間を利用してもう一回確認ですけども、このテクニカルチャレンジという競技は、実際のロボットあるいはシミュレーション上のロボットをただ動かして規定の課題を解く、規定の課題にチャレンジするという、昨日までに行われた規定競技とは違っていわば自由演技のような競技になっています。学術研究の発表というスタイルまではいかないとしても、未来の可能性としてこういうシステムがあると日常生活支援ロボットがより向上するんではなかろうかというような提案であるとか、その提案に対して今各チームが作っている開発しているロボットのソフトウェアハードウェアも含めて、また単にソフトウェアの中でシミュレーションの中で動くっていうだけではなくて、最近のホットトピックでもあるサイバーフィジカルシステムであるとかメタバースであるとかシミュレーション VR、AR、XR そういうような技術を活用してどのように日常生活支援ロボットの機能が向上していくかという将来の姿を提案して、それに対して各チームがどういう取り組みをしているのかということをプレゼンしてもらう。そのプレゼンの中の提案性であるとか、新規性、そういうものを評価していくという競技になっています。また今回アジアパシフィック大会ということもあって、一応というと変ですけど国際大会ということもありますので、各プレゼンテーションはすべて英語で行われるということになっています。審査員の先生方も、日本だけではなくて海外からも審査員の先生方に加わっていただいているという状況です。最初のカメライダーはマレーシアからの参加で、2番目3番目は日本のチームですけれども、英語でしっかり頑張ってプレゼンをしてもらうという形になっています。はい、あと1分ほどでスタート時間ですけど、特に問題ないですね、ソビッツのメンバーは。はい、アカウント2つ入れてますけど、2つとも使いますね。この2つで大丈夫ですね。はい、わかりました。ではもう少々お待ちください。あと40秒ほどですね。はい、
すみません、ソビッツ2つアカウントを使うんですけど、途中でデモンストレーションを挟むので、画面共有を
画面共有は、はい、自分たちでそこはオペレートしてください。普通に我々はズームを見るだけですので、はい。はい、それでは10秒前になりました。はい、準備お願いします。では5、4、3、2、1、はい、ではスタートしてください。
We, Team Soviets, begin our presentation titled, What is the best instruction for human navigation? 何で映ったの？画面共有できてない。Human beings often face situations which require us to decide where to go, which train you should get on, or where to go to get what you want. I suppose we do not get worried too much because various systems support us to reach destinations in our modern society. For example, tablets in bookstores tell us where each commodity is placed. In some stations, the guide robot tells you what to do when you get confused, and the car navigation system lets you know how to get to a destination. Although these systems are indispensable in our lives, instructions from many of them are still not precise. Human navigation, which was held yesterday, focuses on the precision of instruction. In the task, a robot instructs a person to take a target object and carry it to the correct destination by a natural language in the VR environment. In this picture, Kanjus is mentioned, but as you know, this is not enough to get a high score in human navigation. In this task, whether the person correctly grasps the object, whether the person carries the object to the correct destination, and how fast the person accomplishes the task are scored. Therefore, the instructions should include not only the object name, but also its direction and distance. When you give an instruction, you would come up with various sentences with the same meaning. To tell a person which to direct, you can say turn 90 degrees right side, turn right, turn 3 o'clock. Although every sentence has the same meaning, the instruction sentence should be clearly understandable because accuracy and immediacy are required in human navigation. Then, we compared which expression of the sentence is the most understandable to get a high score. In this experiment, we compared three methods of instruction: direction-based, clock-based, and angle-based. With clock-based, you are able to mention 12 directions in total, so it can provide more precise information. However, this method would take more time as it is not a familiar method to tell directions. In direction-based, you can mention 8 directions in total by combinations of front, backward, and right, left. Although this method seems the most intuitive, the method possibly is not accurate because it does not include numerical value. Using angle-based, you are able to convey directions the most precisely. In contrast, human beings are not able to accurately turn to the direction. Consequently, this method is still not perfect. Each method has both advantages and disadvantages, so we compared these methods to find out which is the most appropriate. We instructed 45, 90, 135, and 180 degrees in direction-based and angle-based. In clock-based, we used 30, 90, 150, and 180 degrees. This is because with a clock base, we could not mention 45 degrees and 135 degrees. We provided 12 random instructions to 10 subjects. We measured the time from giving instructions to the end of the move and the angle differences between measured angle and instructed angle. We used a simulation environment in Unity for our experiment. There is a whiteboard in front of a subject, and the subject is asked to rotate based on the landmarks on the board. The subject wore HTC Vive Pro devices and were immersed in the experiment. This is a short movie of the experiment. At first, a subject stands in front of a green landmark in the VR environment. Then we give an instruction. We start measuring time at the beginning of the instruction. When the subject says yes, we finish measuring. Each subject repeats the step for 12 times. These box blocks respectively indicate angle error and the turning time of the three types of instructions. About angle errors, although we did not confirm a significant difference, the average error due to angle-based instruction is a little larger than other two types. In addition, with the angle-based, some subjects misunderstood the instructions. While about turning time, direction-based has a positive significant difference compared with clock-based and angle-based. Direction-based instruction takes shorter time than other two types of instruction. Based on the result of the experiment, direction-based and clock-based instruction became the finalists. Now, considering accomplishment time, we conclude direction-based instructions are the best for human navigation because direction-based instructions do not require much time. Clock-based instruction can provide as accurate information as direction-based instruction. Therefore, we consider that, aside from the competition, clock-based instruction is also applicable as a navigation method.
Okay, then let us introduce a demonstration of our experiment. So we will change our display. In this monitor, a subject now tries to follow the instruction by robot, and we will do three instructions, and all of them are almost the same, but we use angle based and clock based and direction based instructions respectively. So now for the first instruction, we now use clock based instruction. And now the second session starts, and this is direction-based instruction by robot. Robot instructed the direction by front and right, and then the robot now indicates front, behind, left, and it took now it took 30 seconds from beginning at the beginning of the instruction to the end of the task. Finally, the instruction provided by robot is angle based. So now 30 degree to the right, and press the blue glass, and 120 degree to the left, and put it on the trash can. And it also took 30 seconds for accomplishment. So for the first instruction, it took 40 seconds. So clock based clock-based instruction is a bit take a bit longer time for by the accomplishment of the task.
Through our presentation, we evaluated which was the most effective method to tell directions on human navigation. We compared three instruction methods: direction-based, clock-based, and angle-based. Finally, we concluded direction-based instruction is the most appropriate for human navigation because the instruction is the most accurate and requires the least amount of time. We used direction-based instructions in this year's human navigation competition. And we took first place in this competition with a score of 562 out of 808 points. Thank you for listening to our presentation. I appreciate if you have any questions and comments. Thank you.
Hi, thank you for your presentation. Is it the end of presentation?
Yes.
Hi. Okay, so we'd like to go ahead for the Q&A session. Please turn off the share screen mode, okay? Or you can continue to use the slide according to the question. Okay, じゃあ、5 minutes question Q&A time is start. Okay, so please start the question time. Do you have any question?
I have a question.
Please.
Okay, so I understand this is a human navigation, right? So what is the real applications of the human navigations in the real life rather than get a high score in the competition?
So okay, thank you for your question. And yes, what we did in this presentation is only in the VR environment, but we also consider that this guidance this instruction method is also applicable in the real world because the instruction is in the instruction natural language is used, which is and as natural language is used in the real world, so this instruction can be applied to the real world, we consider. Is that okay?
Thank you.
I thank you. So are there any questions? Noda sensei? Please, hi.
Okay, so for further research or application, so I think you need to apply this method for the sequence of navigation or combination of navigation. For example, turn right, go ahead, and turn left. It is a sequence. In this case, the problem is that how to indicate the absolute angle or relative angle. And do you have any idea about to represent and measure this kind of combination of the instruction?
So thank you for your question, and for this experiment, we used absolute angle from based on robot position. So actually the subjects had to confirm which direction the robot faced. But this is we consider that the using absolute angle is relatively fair for all for all people, because if we use relative angle from based on subject, every time the robot or instructor has to detect which direction the subject faced. So it is a little bit complicated and more sometimes not clear. So we consider using absolute angle in the real world or VR environment is more effective.
Okay, thank you very much.
Thank you.
A short question. Do you have short question within 20 minutes, 30 seconds?
Too short to ask.
Too short. Okay, 3 seconds, 3, 2, 1. Hi, thank you for your presentation. And, OK、じゃあ、ソビツ、どうもありがとうございました。それでは、次のプレゼンまであと1、2分ありますので、ちょっとお待ちください。で、次のプレゼンターを、メインのところに持ってきます。よいしょ。はい、3番目のプレゼンはイレーザーズのチームになります。イレーザーズは今、2人入れましたけども、この2人で大丈夫ですか？聞こえますか？はい、
大丈夫です。
はい。じゃあ、プレゼン開始まであと50秒なので、スタンバイお願いします。待機室にもう1人いますけど、この2人でいいですね。イレーザーズ。
はい。
はい。
もう1人ですか？
うん、合計3人で入ってるけど、3人入っちゃダメなので、はい、私がもう2人に絞りました。はい、ルールで2人までですので。
OK です。
はい、10秒前です。5、4、3、2、1。はい、please start。
sorry, switching, change member. すいません。メンバーを変えることはもうできないですか？ズームの方の。
変えますか？まあ、時間は使いますよ。
はい、大丈夫です。18338001になってることを、はい、ショーン、別の方に切り替えてもらっていいですか
？1833を抜くんですね。はい、で、誰を入れればいいですか？
ショーンですね。イレーサーズのショーン。
ショーンさんは来てないですよ。良平さん。
良平さんでお願いします。すいません。
これでいいですか？
はい、大丈夫です。
じゃあ続けてください。
はい。Hello. We're from Team Erasers. Thank you. Sorry. So, sorry, my bad. So,
for our technical challenge, we focused on ways to develop better algorithms through VR. So a really good way to develop these algorithms are through competitions and tournaments such as this one, RoboCup. Some other examples are Kaggle, and these tournaments and competitions are very effective because as rewards they offer rewards and prizes for people who get into first or second or have very great algorithms in their programs. So this is a reason for them to make these algorithms effective and more better. But there's a bit of a problem with these competitions, and that one is that building robots on the hardware level and the test fields for them is very difficult. So for robots hardware, you'd have to gather the parts and then assemble them. And for test fields, you would have to find and make you have to find a big area and then set up the field to simulate an actual simulation that you'd want to test your robot in. For this, using VR, you can simulate the area and the robot to work in. So not only do you not have to be able to gather all the necessary parts or the field that you want to work in, you can also gather the data from the VR testing and use it for later programs and also evaluation, see how you can improve on what you built so far. However, there's still a problem in which that the software for programming these robots and algorithms is also very difficult. So we made a VR simulator that also works with a scratch editing tool where the scratch editing tool will transfer the code, the blocked code, and turn it into a ROS engine, and then send it to Unity that would also then connect the user to the field. And that way, people who aren't that familiar with programming code is also able to make these algorithms and systems for robots. So in Unity is the previously mentioned robot hardware and field system. Both of those will be handled within Unity, and the software side will be handled by Scratch. We created the top area, the Scratch editor and the Scratch server part, where you can connect blocks from the Scratch editor, and then that data will be sent to the Scratch server, which will then be transferred into ROS code. And then the ROS code will be sent back to the Unity side, where the human will be connected and then can interact with the robot that you programmed. So here we would like to demonstrate an example of that. Please switch screens.
Okay, please wait to. Hey, please wait. Go straight. Start to demonstration. Now, first in block editing. This block is receive lost topic.
Sorry, one moment. Okay, sorry. So I will explain from here. So the first block will receive the message from the operator or whatever topic that you set it to, and then we'll turn it, put that variable into a different separate variable that we can then use in our program. And then through the if statement, we can make conditions on how the robot will work. So if the variable that we have made contains the method start follow, it will start the program inside that if statement, starting from say start follow you, and then the next block, which will start the follow me program that is previously made for Scratch. And then the bottom if statement is for when you want to stop that follow me program. If the method contains stop follow, then the robot will say stop follow you, and then turn off the follow me program. The block on the right with the flag and says start from operator, that is to subscribe to a topic that's necessary so that the program can receive those topics and messages. So like this, even if you're not very familiar with the programming of ROS, or maybe the node systems for ROS, with these blocks, you can easily connect what you want to make and make conditions in. Through this, you can have the robot move in algorithms or such. Sorry, you can program your robot very easily, even as a beginner. So here the program has started. So now that the program has started, once the user moves, the robot should follow him. If you can see on the right side of the screen, it says Unity, and in brackets it's VR. That is the screen inside the Unity system, which will have our user, the human user, and also the robot inside the screen. And under that is what the robot sees. So apparently our program isn't working. Maybe there's some sort of malfunction, but yeah, so if this were to work without problems, again, you can simulate how your robot would work and interact with the other person in the VR environment. Right. Sorry, one moment, please. Okay. So unfortunately, it didn't work, but that is the concept of our solution to this problem. There are other related work similar to this. The one on the left is a project called Virtual Home, where people can, in a similar way, connect blocks in a certain way to make human movement, or how people would, an example, move around the house to complete certain tasks, like make tea or such. And on the right is a project where they try to train robots to understand the meaning of human speech languages. And through that, when you can talk to robots, sorry, the goal is to talk to robots and or give them certain tasks in the human language instead of the programming language, and that will help let them complete the task as they will understand. But both of these projects aren't that focused on the human to robot interaction, and that is where we think our project is a little bit different, because through our project, we can, again, the humans can easily make the algorithms and systems of the robots, and through the VR capabilities, we can record the reaction or the interaction between the human and the robot for future projects. So for our contributions, for the robot competitions, with the system, teams can more easily develop and create robot systems and algorithms for these tournaments. And they can more easily create these systems. And this will also lead to more newer teams, beginner programmers, to start programming their own algorithm and code for these robots to work with, and then join these sort of competitions with everyone else. Another use for this system is that with the Scratch to ROS system, it's also we can also make a junior league for these already existing platforms, such as the education or the FBL area. Those platforms have the normal writing code, and that is very difficult for beginner programs to start learning and then understand, and then finally enter these competitions. But with our system, they can go straight into connecting the blocks, and then set the conditions and also algorithms for the robot system. My apologies. So other than that, as a whole, what we think is very beneficial for this is that, again, many people can start programming and making these algorithms and software for robots, and then interact with them through the VR system. And using the previously mentioned VR data collecting system, that we can share that with everyone else, and then people can use that information, data, to create more interactive robots in the future. That concludes our presentation. Thank you.
Right, thank you. So just 15 minutes is past. So please go. Let's go ahead for the Q&A time.
Okay.
Hi. Do you have any questions from juries? Hi, Amy Sensei, please.
I have a question. So, if the demonstration worked, what was supposed to happen?
So if it did work, one moment. Can everyone see the slides again? Sorry, one moment. So if the the demonstration did work, as the human inside the VR environment walked, the robot would follow the human. And thank you. So the follow me function already exists inside this system. And so if people wanted to make an algorithm or robot software that utilizes this follow me system, they can easily do so with this. So as I mentioned, this model here is where this is the model that that's used for the human wearing the VR set inside the environment. And it's very hard to see, but this robot, this HSR robot inside the VR environment will follow after the human. It's also it's not just taking the position of the human model either. It's actually looking for the model's feet and then going after that. So the inside of the program is also not very similar, but it's the same as what's actually being used in real life robots. So people can test their robots inside the VR system and then use it in real world robots. Hope that.
So the operator is the human.
Yes.
Is it?
Yes.
Then the human has to give a instruction, right, at the beginning.
Yes. For that, for our version currently, we have the human, the operator, press a button on the controller. But in the future, we couldn't make it in time for this demonstration, but we were trying to implement a speech-to-text system where you can speak, and the microphone inside the VR headset will take what the user said, turn it into speech, and then turn into a text, and then send that to the robot for the robot to use. So if we were able to do that, the if statement saying the message contains "come here," instead of that being a button, the user could say "come here," and then the robot will then start the follow program.
All right. Thank you for the clarification. Thank you.
Thank you. Are there any other questions regarding our project?
Hi, Noda Sensei, please.
Okay. So I guess your system or design is focused on the interaction rather than the control of the robot itself. And in the interaction, so the necessary factor is parallelism and interruption. And is it easy to represent this kind of parallelism or interception in Scratch or such kind of visual programming, or do we need additional facilities to handle this kind of things? What is your plan?
So sorry, for clarification, you're asking about the requirements for using our system. Is that correct?
System and your plan.
So the requirements are actually very simple for this. If you have one computer, a gaming computer to be specific, or any sort of strong computer, you could have the ROS and Windows system on one computer and then work locally on that.
The question is that not the performance of the computer.
Sorry, the question time is over.
Okay.
I'm so sorry.
Okay, thank you for your presentation and the questions. Hi, all the presenter has been finished the presentations. So we are now going to the evaluation phase, but it might take several minutes. So the final total score and the final result will be shown in the web page of the RCAP2021. So please check the final result of the technical challenge. Thank you for your presentation. ですね、ちょっと審査は少し時間がかかりますので、このライブストリーミングは一旦ここで終わりということにしてですね、残りお昼過ぎぐらいになるとは思いますが、ホームページの方で結果の方は発表したいと思います。それでは審査員の皆さん、今日はお忙しいところありがとうございました。プレゼンターの方もありがとうございました。じゃあここで一旦ライブストリームは一旦終わりということにしたいと思います。それでは皆さんYouTube ご覧の皆さん、どうもありがとうございました。結果についてはまた後ほどホームページでご覧ください。はい、それではライブ中継終了させていただきます。ありがとうございました。それでは。